this computer. Okay, welcome everyone, and big thank you to Bob for agreeing to present on this very interesting topic. I won't bang on, I'll hand straight over. Over to you, Bob.
Okay, thanks very much. So thanks again for the opportunity to chat about this topic. I'll just start off by reminding you that some of the things I might show are not really for the do-it-yourselfer. You really need to be very comfortable working with AC on some of these things. On others, not so much. But the idea of this talk is not to show you how to do everything. It's more about enabling you to get enough information so you can talk to your shed Sparky or commercial Sparky about what you might like to try with these devices. Not all Sparkies know about them. I would have thought younger Sparkies, but not so much even younger Sparkies. They might have heard of them and have a limited understanding of what these variable speed drives can do. I'd also like to point out that electrocution is the leading cause of death amongst do-it-yourselfers. So just bear that in mind if you decide to fiddle. And also that I'll go through a bit of theory and then show you some examples and then do some applications. So let's start off by saying, well, what is a variable speed drive? Well, I've got one on my bench over here, and there it is there. This is a mid-range product from Powertran in China, but they come in all shapes and sizes, from about the size of a fist through to the size of a refrigerator. And I've got one over here. It's on the floor there, and you can just make it out there. That's an industrial grade 7.5 horsepower VFD. This one here is a 3 horsepower VFD. And what they basically do is convert single or three phase of a certain frequency to three phase of the same or different frequencies. And this enables the speed of motors to be changed. So I'll just quickly demonstrate one running. So, oh great, I've just knocked over my coffee. Luckily it missed the laptop. This is the motor that it's hooked up to. So it's mains to VFD, VFD through the orange cable to the motor. So we'll start it up, or firstly turn it on, and the speed with which they turn on varies. Now I'll bring this in closer so you can see it. And I'll switch cameras so that I can get. So here we've got the VFD, and it's displaying 51.04 hertz. So the mains frequency coming in from the power supply is 50 hertz, and it will output 51 hertz of signal. So I'll just back out and just show the motor. I'll just show my mess first. That's what I just did. So I'll start it by pushing the run button, and you'll see the motor spin up. And you can see it's not spinning up super fast. Got it set for a 10-second acceleration time. So now it's up to 51 hertz. And to stop it, I just push that button, and I'll point to the motor, and you watch to see how quickly it stops. And if you heard a little squeal, that's normal. That's because I'm making it stop. Sorry about the jumping around here. Let me just switch back to the other camera. Here we go. And you heard it. If you heard it squeal and stop really quickly, that's because I programmed the VFD to actually do that. And so that's basically working in action. And I haven't shown you the frequency changes yet, but before I do that, I'd like to do a little bit of theory. So now I'm going to pick up the camera again and show some slides on the screen. And I'll switch the camera over. And take that back. Okay, so this is a block diagram of a VFD, what a VFD does. It takes the AC, I'll use the mouse if I can see it, yeah. It takes AC mains in, it rectifies it, converts it to DC, and then the DC is set up so there's positive and negative versions of the DC, not just positive to 0. It's then chopped. Where's my mouse gone? Here we go. The signal is then chopped, turned into a series of pulses like that, and then modulated and reconverted back into a sine wave of a frequency determined by the operator and the modulator. And then it's output as 3-phase. Now that's in words, and maybe this is a more useful diagram. So we start off with AC mains coming in, and then the voltage is then turned into DC, and then it's chopped and modulated and turned into a 3-phase signal out. So red, green and blue represent the 3 phases. This next one is the same diagram, but what I'm showing is that the modulator is changing the frequency. So the space between the peaks of the AC, this is the electrical current, the AC mains, is, see that distance there between the reds is reduced over here. So it's a smaller wavelength or a higher frequency. And that's the real power of the VC, is you can control the frequency and that controls the speed. One of the limitations of VFDs is they don't have constant power across, they don't allow the motor to develop constant power across the full range of the frequency. So here I'm showing a graph where the vertical is power and the horizontal is frequency. And normally we're operating at 50 cycles, and the motor is arranged to deliver its maximum power at 50 cycles, or 60 if it's in the US. Now, when you use a VFD, unfortunately, the lower revs means lower power. And so the blue line is the theoretical power line, whoops, for a VFD. So in theory, you have proportional power along here. In other words, when you go to half the frequency, you go to half the power. If you go to a quarter of the frequency, you go to a quarter of the power. That's the blue line we're referring to. And up here, you're supposed to get constant power up to a point where basically friction in the motor slows you down. Now, that's theory. In practice, it looks more like the green line. You need some frequency just to start the motor. It might only be 1 or 2 hertz, but the motor will have very little power, and you might even be able to stop it with your hand at that point. And then eventually it hits the proportional line. And then up here, as I said before, as you go further into higher and higher frequencies, the power drops off because the friction in the bearings, and air friction and magnetic friction is another one, will stop the motor. There's another reason that you can't go indefinitely all the way up here, and that is that the bearings in the motor and even the physical integrity of the rotor will restrict how far you can go. Most conventional motors, once you get to about 150 hertz, the frictional forces, the bearings and the rotor will start to cause problems, and you're at your own risk if you decide to go above that, and the motor might not let you go above that because it just says, no, I give up, I can't do it. Now that's the conventional VFDs. So they're called voltage to frequency VFD. There is another kind of VFD called a vector drive VFD, which is what the red line refers to, which has a much better power profile. So you get some power almost instantaneously, and you can basically get about double the power at low frequency and get your maximum power very, very close to the maximum power at about 80% of the nominal maximum frequency. And this part of the curve over here doesn't change all that much. So the vector drive VFD, and they're nearly all having vector drive capability these days, is the way to go. You can, if you buy a very cheap VFD, you're probably only going to be able to get a V2F, the green one. And so you need to pay a little more to get these ones here. But these are almost all available. They do require some extra programming. Okay, now a little bit about motors. So three-phase motors come in two connection forms. One is called the star, which we represent by the symbol Y, where the coils are wired so they have a common point in the center, and the power is connected to 1, 2, and 3, like that. Then the second form is the delta, and the delta is wired in a triangular diamond shape, triangular pyramid shape, and once again the power is connected to 1, 2, or 3. Now, this is very important if you decide you're going to convert a three-phase motor so that it can run on a 240 volt VFD. If you take a 415 volt star connected motor and connect it to 415 volts, you'll get full power. That's what the FP stands for. If you connect it direct to the output of a VFD, 240 volt VFD, you'll only get half power because it only operates at 240 volts. So that motor, that particular motor, has to be converted to delta. So the motor is converted from a Y to a delta, and this is standard form. There's not a fudge. There are lots of motors made both in Europe and North America that are made in this format, and when they're converted over, they can work on the other voltage. So a 415 volt star connected motor converted to delta, if you connect that to a 415 volts, you'll have problems because it's not designed to run as a delta form, in delta form on 415 volts. However, if you connect it to a 240 volt three-phase power, you'll get full power. So that's a 415 volt motor, star connected, converted to delta. That's the one you want to run on a 240 volt VFD. If you have a 415 volt and it's delta, it'll run full power on a 415 volt, but only half power on a 240 volt. If you connect that to star, you get less power still. A 415 volt delta connected to star turns it into a 690 volt motor. So there's really only one point on this chart that works for the 240 volts. It's a 415 volt motor. It has to be Y connected, and you have to be able to connect it, convert that to a delta, and then you can use it on a 240 volt. But most modern motors will have that capability, and I'll show you that in a moment. Here's an example of a motor label. This is 1 horsepower, 0.75 kilowatt, 1410 revs per minute on 380 or 380 to 420 volts, that'll be. You see it's a star connected motor. All right, 380 to 420. On 220 or 220 to 240, it becomes a delta connected motor. And so this one here is very easy. You just move some brass strips around in the connection box and you'll turn it into the right form. And this is typically what they look like. So when these brass strips are connected across the top here and power is supplied in here, that is a star connected motor. If those brass strips are moved to be across here, that's only across here, not across there and across there. In the green in the green setup, that's a delta connected motor. And if it's 415 volts in the Y connected or the star connected form, it'll be a 240 volt in the delta connected form. Now, what happens if your motor doesn't have this? Then you run into headaches. So what has to be done is that the motor has to be opened up, and that junction has to be found and broken open and connected up like this. So that point there has to be connected onto there, that point there has to be connected onto there, and that point there has to be connected onto there, just like this one here. This is a star to delta conversion. Now, I've done about 30 of these and haven't had one failure yet, but this is a job best left for a motor rewinder or a competent electrician can do this. You're opening up the motor, you've got to pry open the coils with a hot air gun and plastic tweezers sometimes, and find this point, disconnect it and reconnect the wires up and so on. So they're the main electrical issues. I'll put it back on the other camera now and just briefly talk about mechanical issues, because what happens is that because of this half power problem, when you're down at 25 hertz, the half power means you've lost power. So to get around that, a simple way is to just increase the size of the motor. So if you've got a 1 horsepower motor on a, say, drill press, and you want to be able to operate at low revs, it's not a bad idea to increase the power to 1.5 horsepower or even 2 horsepower. Now, as soon as you do that, you open up a can of mechanical wounds. And the first one is you'll almost certainly have a different size shaft on your motor. So you might have a 19 millimeter shaft on the 1 horsepower. If you go to 2 horsepower, you probably have a 24 millimeter shaft. So then you either have to doctor the pulley or doctor the shaft, and that's a nuisance. There also could be mounting issues. The feet and the location might not quite line up. So there's that. There may also be physical space issue. The space for the motor, for a 1 horsepower motor, where your drill press is or under your lathe may not be suitable for a bigger motor. So you may have to outboard the motor and things get complicated. So there are electrical issues, there are mechanical issues, and I just want to talk briefly again about this problem of when you go to low frequencies, you get less power. So if we start off with a, say, a 3000 or 2,880 RPM motor, and what's the highest we can take it? Well, if you double the frequency, so you go to 100 hertz, you get double the revs, 5,700 and something revs. Now, on a cheap Chinese motor, that could be the limit of its bearings. So I wouldn't be taking it up to 100. If it's a good quality motor, you may even be able to go to 7,000 RPM, but you'll have problems. You might have problems with the rotor mechanical stability and also something else called magnetics. The motor will start to squawk and squeal when you go at high revs, and that's an indication that the motor magnetics are not working all that well. At the low end, when you go to, say, 25 hertz, so you'll then be operating at 1440 RPM, that's fine, but you'll have half power. If you double the power of the motor, you'll be back to where you were. So for full power operation with a 2880 RPM motor, you can go from about 25 hertz up to, 75 hertz, maybe 100 hertz. So you've got about a 4-to-1 ratio of speed. If you use a 1440 RPM motor, so it starts out at 1440, and you go to 100 hertz, you're only operating at 2880 RPM anyway, and so the bearings will be fine, the rotor should be fine. You could even go up to 120 or 150. Some people take to 150, although those other issues come in as well. So from 25 hertz up to say 150 hertz, that's a factor of 6. So you've got 6 speed. If you are doing mainly small work or light work, you could go down to maybe 12.5 hertz. You'll only have quarter power. But if you double the motor, you'll have half power. And if you use a vector drive VFD, you could have 3/4 of the power. Now, that's fine. So you go from 12.5 hertz up to 125 hertz. That's a factor of 10, which is really fantastic. But you've got to be really careful about operating at low speed because the motor isn't turning as fast, the fan isn't cooling the motor as fast. So you can only use it for short bursts or light work. Or you could add an extra fan onto the outside. But you just need to be aware of this, that you can cook your motor at low revs. I mean, on a drill press, we don't tend to operate. Drilling is a short-term operation. I operate my drill press down as low as 7 hertz, which sounds ridiculous, but I do, because it's usually, you know, 10 to 15 second burst, and then the motor run. Then you increase the speed of the motor, and the motor cools down. Same on lathes. But if you're doing heavy cuts on a lathe for long periods, you have to be sure you're not overheating the motor. So the speed range is really depends on the work, the motor, and a bunch of other things. So you have to take all those things into account. But don't expect on a, say, something like a metalwork lathe or even a woodwork lathe to completely replace all the speeds. You may occasionally have to change the speeds if you work at both very high revs and at very low revs. You're not going to do that at the same time, but you just need to be aware of that. So that's a complication that a lot of people think, I'll just get a VFD and it will solve all my speed problems. Unfortunately, it won't. Let's get back to the actual VFD itself. I'll just move that over. This VFD, let me just also turn the camera around. This VFD is a particularly nice one from Powertran. It's a mid-range VFD. It's got 2 displays, which is very useful. This is showing the frequency, and when I start it up, you'll see the speed increasing, and this is now displaying the current, the electrical current being drawn. This VFD has very good, very solid connectors and very easily and well laid out control connections under here. This is where you would connect up to do things outboard. This VFD also, this panel is removable and it has memories. So you can store machine parameters and then pop it out and go to another VFD, plug it in and copy everything across. It's a very elegant and well thought out VFD. Now let me just do a quick turnaround here, put you on the motor. And I just want you to see it stop, how quickly it stops. So it stops in 0.3 of a second, and that is not something I would recommend that is done every day. Could be useful just as an emergency situation. Can make it stop even quicker, but it's very hard on the bearings. And this VFD has the braking circuitry built into it. Not all of them do. The cheap ones don't even have and don't even come available with braking circuitry. And so if you're ordering VFDs and you want to be able to brake, it needs to have it in there. Now, to stop it quicker than the 0.3 of a second, you can add something additional. Let me just get it out from the back here. What you add is this electrical brake. And it's just a big resistor with known resistive characteristics. And these are connected onto these connections in here. And then you can make it stop very, very quickly. And a machine with a big inertia, like a big bandsaw or a big circular saw really benefits from something like this. At the men's shed, we had at Manning we had a circular a radial arm saw that was taking about 120 seconds to stop, and the management asked me to look into a way of cutting that time down. So I installed a VFD with one of these brakes on it, and we started at 10 seconds, and I had no trouble stopping it at 10 seconds, and we took it down to 5, and then we took it down to 2.5, and at 2.5 it started to squeal, and there's a possibility you can loosen the locking mechanism if you brake the motor too hard. So we settled on 4 seconds. So from 120 seconds to slow down, and during most of that 120 second time, it was deadly silent, so really dangerous, to 4 seconds. And you can buy an electrical brake that doesn't have all the other features of the VFD, and use one of these, and they're a bit cheaper, but not that much. It's just easy to buy a VFD, and then if you decide to offload the saw, you've got a useful VFD device. Okay, so maybe just a little bit now about the sort of testing I do on motors. And you may have noticed this strange apparatus that the motor is set up in. This device is called the Prony Brake, and it's a horsepower measuring device invented in the 1700s by a Frenchman called the Prony, who used, instead of a metal pulley, he used a wooden one. He used a rope as a brake, whereas I use a steel strap, and I'll just hook that up. And it just basically provides a brake drum type operation on the motor. So now this is hooked up, and these two things here are luggage scales. And so these two measure force or weight, mass, which is a fundamental quantity, and the brake acts on the pulley or the flywheel, and the radius of the flywheel times the difference in the weight or the forces gives you the torque of the motor. And here we've got a little, oh, maybe I'll bring this in a bit closer and switch cameras. So here we've got a reflective marker, and I can put an optical tachometer on there. So as this goes around, the optical tachometer can measure the RPMs. So I've got the torque and the RPMs, and that can be converted into a horsepower. So this is a horsepower meter, and I use it to test all the electrical motors that I modify, and that way I know whether they're working properly, and also I get to know the characteristics of the motor. Now I'll just start it up. To get the horsepower, to get the power rating, you have to provide a back force, and the back force is provided courtesy of this handbrake. And you notice that when I lift that, it actually, when I apply the brake, it actually pulls this on and provides difference, increases the forces on the wheel. I'll only demonstrate this once because it actually does strain the motor to do this, and I don't particularly want to do it because it's only a very small motor. I'll just start the VFD. And now you can see it makes a bit of a racket, and you can see there's differences in the forces. This is 1.8 kilos, and that's 0.1 of a kilo. And then now what I do is I apply the brake, and you'll see it slow down. And I won't do that too much because it does long term. If I do this all the time, it'll damage the motor. So I have to capture that weight, and the RPMs all at the same time. And to do that, I actually just set up a little, I could computer interface all these, but it's easier. It's a lot easier just to put a digital camera on a tripod. And what I do is I click the button on the tripod, apply a bit more of a force, apply a bit more of a force, apply a bit more of a force, and when the motor stalls, that's the maximum horsepower of the motor. All right, just get this back onto the other camera. Have we got our moderator there?
Yes, yes.
Now might be time for some questions before I go on to some applications.
Yeah, good point. Gary, Garvin, do you have any questions that you'd like to raise?
I'm only barely keeping up with what Bob's talking about. So no, I don't have any questions.
Yeah, sorry about that. It'll be the second half where I'll go around to some machinery and actually show you them being set up, how they're set up, is probably going to be of more use to you. Yeah, I'm sorry about that. But anyway, maybe Garvin's got a question.
I suppose, is it just mainly for speed control? Essentially, the primary function is a speed controller. Yeah,
I'll talk about that when I go around and do the application. So it is primarily speed control, but it's the side benefits of speed control that have other ramifications as well. And automation, you can set things up to be automated, but that doesn't really apply. That's an industrial application, doesn't really apply to, say, a men's shed situation. But yeah, it is primarily you get control of the speed, and then that allows you to control a whole bunch of other things.
Yeah. So some of the motors that come with inbuilt speed controllers, are they using a VFD type electronics?
Yes. I've got a cousin in northern Italy who makes electrical motors, and one of his biggest sellers is small three-phase motors with built-in VFDs that can be connected directly to single phase. Okay. And I notice even here in Forbes sell at some expense a similar motor, but theirs is a Chinese-made one. My cousin believes that in 15, 20 years' time, there won't be any single-phase motors. They'll all be three-phase motors with micro VFDs built into them because of the benefits. The benefit of a three-phase motor is they use less power. They're 5 to 7% more efficient. Now, that doesn't sound like much, but you're talking about tens of millions of motors right across a country, Europe or North America. That's a lot of watts you save. And so all motors will eventually become three-phase. And then you can you decide whether you're going to drive it by three-phase or with a VFD and single-phase. I should add that most VFDs are actually three-phase to three-phase VFDs used in industry. So, for example, to control the speed on a large processing conveyor belt, it's a perfect device for that. And they're everywhere in industry, and they're all three-phase to three-phase purely to get the speed control, not about the phase conversion. Benefit for men's sheds and home people who don't have three-phase or don't have three-phase where they want it, because that's a really significant issue. You might have a three-phase machine and you might want it in that corner of the shed, but you don't have a three-phase power point over there. Now, I don't know if you've looked up the price of three-phase power sockets, but they're very expensive. Then you've got to run a dedicated line, then you've got a dedicated breaker, and then you've got to get a qualified sparky to put it in. That's a lot more than $100 that a VFD will cost you, provided all the mechanical and electrical issues can be solved. So it's the swings and roundabouts. If you have to pay for a sparky to put in the VFD and you've already got three-phase, I would just pay them to put in another three-phase plug and socket. But if you can do some of these things yourself, or you have the need for the speed control, then I'll definitely go with the VFD. There's no doubt about it. Having three-phase power, if you've got it, then use it, and you don't have to muck around with all these mechanical and electrical issues. All right, any other questions?
Well, so I mean, my primary interest is, of course, to control our felder, to automate it using a VFD.
Yeah. So and that's a really good example. A dust extractor going at 50 hertz, if it's able to go at 60 hertz, that's a 20% increase in flow. That's a cheap, that's a couple of $100 solution. And not only that, you can automate it. You can then connect it up to auto blast gates. You can run it at different speeds. I was at a men's shed yesterday where they were running at 50 hertz, and then when no one's using it, they just drop it back to 40 hertz and use it for shed ventilation, which is what I do myself.
Okay.
All right, what I'll do now is I'll walk around the shed, and this time I won't have any Wi-Fi issues because I put in a nice Wi-Fi base station down here, which I needed to do anyway. And I'll start over here. I'll just switch cameras. This is my little Hercus lathe, which I was very fortunate to get for nothing because it was 3-phase. And the first thing I did was I converted it to VFD. Now I'll just show you over the back. The motor is non-stock. That's a 1 horsepower motor. Originally it was a 1/2 horsepower. It's only a baby lathe. And that's to get around this power problem. Now the VFD is inside this enclosure, and I'll just open it up. And it doesn't need to be inside this enclosure, but it was the first one I did. And I heard you had to be a bit careful. If you recognise the enclosure, it's actually a Black & Decker toolbox dust extractor. So there's the VFD. You can see it's not very big. It's another Powertran. Let me just put a light on. That's better. So it's a Powertran VFD, not very big as you can see. This is a 2 horsepower, but I've current limited it to 1 horsepower. And it's got a fan. The enclosure has a fan because I was worried about needing to keep it cool. And the controls, there's no controls on the front there because the controls have been moved to the front of the box. Let's get this set up. So the controls are on the front of the box here. I'll just turn it on. And this is a very nice VFD. It boots up very quickly. I've also added a tachometer to the lathe, and the head of that tachometer is here. This is the magnetic sensor, and I'll just rotate this by hand, and you can see the magnet. That's a little magnet that's just stuck there, picking up a bit of swarf. And every time that comes around, where is it? You can see the LED blinking, right? And currently this is set up for 84 hertz, which is a bit high. So I'll back it down. I'll back it off. As this is really a really useful feature. You know what speed you're going to start it at. So these are the speed control knobs, and this is the stop, forward, and reverse. So we'll just go forward. So it's running now, and I can change the speed, and I'll show you on here. So this is now go up to 100 hertz on this. I'll back down and go very slowly. The only time I switch gears on this is when I use the back gear on the lathe. It has a back gear that allows you to go very, very slowly. And you can go, I'll just stop it and reverse it automatically. I'll just flip it into reverse. Oh, VFD didn't like it. I have to reset it. So forward, reverse. Now, why would you use reverse on a lathe, especially one that doesn't have a chuck that is locked on? Well, I do a lot of tapping on here, and I manually drive the tap in, but to reverse out takes a lot of time to just unwind, and so I just run it backwards. So this also has both coarse and fine control, and with fine control, I'll show you how fine. Let's speed it up a bit. I'll show you how fine you can do it. You can get it fairly fine, and that is very useful when you have a vibration. You might have a little vibrational flutter, and you just want to move slightly away from that speed, and then that will sometimes remove the flutter. So, just to summarise, then, this it was about a $120 VFD and $50 for all the parts, and it had a working machine. It's fantastic. You know, I use this nearly every day, maybe every second day. So it's a good example of a VFD. All right, let's look at the next one, which is the drill press. Now, this is a drill press that I paid money for. It's about 15 years old, and about 7 or 8 years ago, I put a VFD on it. Now, it's got a very fancy looking box here, and it's the same VFD as the lathe. The original motor on this was also this was the 1 horsepower, and I'll just show you around the back. It's a beefy, very beefy 1.5 horsepower electric American Leeson motor. I got the motor for about $30. It was steel. I refurbished it, but they're a beautiful motor, and they have a very good. They work very well with VFDs. Now, the VFD's in a box, and the main reason it's in a box is because I'm very close to where all I do my grinding and shitty work with metal work, and I don't like dust getting into these. So it's a bit over-engineered. It's got a fan in the back, but I went for a transparent cover so I could see the speed and what's going on. So I turn it on with the ordinary switch, and the light works the same way. And so it's active here, and there's the tacho up there, and the tacho head is up here. And start, I've got a pedal and I've got a switch, so I could start it with the switch, or I pedal below, and forward and reverse, and I'm on switch, and so I can go up to or down. You see the speed going down. It takes a while to catch up. So let me just get it on 100 RPM or thereabouts. So it's turning very, very slowly. And now I'll try and stop it. I just cannot stop it. It's a very, very powerful, it's a 1.5 horsepower motor, but this is also a vector drive VFD, and that's very, very strong. So I can drill very large holes in steel with this thing, even at low speed. I sometimes do want to go even lower with a hole saw or something like that, and that's about the only time I need to change the belt speeds. Let's go the other way, go up in speed. So this is set, rattle, it's the top rattle. So it's set for about 110 hertz, 1300 RPM, which is for a big drill press. So if I wanted to go above that speed, I would have to change the belts. So this is a very good example of application of a VFD. The electric motor didn't require any conversion internally. I could do it externally, and it really was just bolting it all together. In fact, after a while, becomes the most annoying things becomes making all these little control features. So if you're happy enough to just change the speed from this knob, that's fine. That's all you need to do. All right, let's move on to this hurdy-gurdy. This is what I call my tri-grinder with VFD, and it's on the grinders are on a turntable and can swing around like this, and you can bring them into position. You can even undo them down here and turn them around. Okay, so this VFD, these grinders are 3-phase, these two are 3-phase. That one over there is single phase, that's separate. But these two work off one VFD. That's a very common question I get asked about, can I put one VFD in my workshop and run a bunch of 3-phase gear off it? Not a good idea. The problem is the VFD and its program is really dedicated to a single motor. And the wire or the connections between the VFD and the motor should not be interrupted by any switches or any other controls. If you throw switches, you have to be very careful. If you throw switches between these two, you can get a loud bang and some smoke. But because these two machines are identical, they're both 1 horsepower grinders, I thought I'd have a go at running them from one VFD. Now, to do that, I can't run them I could run them simultaneously, but I don't. I want to run them separately. So I provide power either to this one or to this one here. Now, to do that, I've set up here a crossover switch, and that provides power to one or the other. But I don't want to be switching that over while the machine's running. If I do that, it's going to cause problems. So I'll just start it up. So I've got this reset, special power on switch, reset switch, and then whichever one this is set on, it's set to run on that one over there. It'll start. Okay. And here we go. And it'll make a racket because these devices here make noises, right? Now, if I want to switch over to the other one and I open this, immediately that stops that motor. Now I can switch it over to there. And if this was all wired, hardwired, me closing that would start that. But I've got a reset switch. So now I put the reset switch on, and now this one here will start. So it is possible, this is a bit quieter. So it is possible to run multiple machines off one VFD if one is running at the same time, and all the machines have the same characteristics, the same power and rotational characteristics. Now, when I turn this off, this will run for ages because it's so heavy. You might be interested in this. These are Cbn wheels, cubic boron nitride, one here and one here. That's a brand new one. And this is a diamond wheel. That's what I use to grind tungsten carbide tips with. This is a standard belt sander, standard multi-tool belt sander. And this is a little thin curve cutting wheel, table saw that I made to cut steel with. So if I want to just dock a little bit off that bar, I can just drop that guard, and this turns at 12,000 RPM when the VFD is at 50 Hertz. So it's a pretty high speed. It's geared up with a pulley. The belt sander, I run it at from 30 Hertz, so about 1500 RPM, up to about 60 Hertz, if you do want to do coarse stock removal. These grinding wheels on this grinder will run at any speed from about 1,000 up to 3,600. At 3,600, they really strip stock away very quickly, but these are sharpening devices, so I tend to just run them at 3,000. So that's an example of one VFD, and by the way, that's one of the first series of VFDs that I bought. This is a Huan Yang VFD. These were about $150 about 7 or 8 years ago, and they were the cheapest, about the cheapest you could get. Incredibly reliable, 7 or 8 years of use in a fairly dusty environment, and not a problem, not a single problem. Now, I've also put a VFD on my bandsaw. This is it here. I'll just step back so you can see the bandsaw. Now, this is putting it on a bandsaw is borderline, but I do a lot of saw milling And I'll just show you the blade I use on the sawmilling. On the sawmill. So that'll give you an idea of the blade, right? It's a serious blade, about 1 TPI. And this runs on a 27 horsepower Kohler-powered sawmill down at Naval Base, that blade. It runs at about 5,000 feet per minute. And most ordinary bandsaws you buy from the wood shops run at 3,000. If you get something like a hammer or a higher end bandsaw, they run at 4,000. But optimum cutting speed for especially rip cutting for a bandsaw is about 5,000 feet per minute. So I wanted to see if I could convert this to run at 5,000 feet per minute. And when we run the bandsaw mill, 5,000 feet per minute generates a lot of heat. So you have to cool the blade with a stream of water. Now, that's not exactly something you do in a workshop, but you don't tend to cut, you know, great long lengths, wide lengths of timber on a standard wood shop bandsaw. You tend to do short cuts, or you might do one long cut and then have a rest. And so the band has time to cool down. So this is, once again, a Huanyang VFD. This is a 4 horsepower VFD. And the motor on this was an absolute bargain. It's pretty hard to see. It's buried down in there. It's a very unusual motor in that it has a fan that runs at twice the speed of the actual motor itself. And so that means I can operate this at low speed. Now, why would you want to operate a bandsaw at low speed? Well, one of the things about this bandsaw is that some time ago I put a foot brake on it. And that foot brake, unfortunately, got in the way of the second low speed, and so I had to remove it. But I thought, I'm putting a VFD on it anyway, and so I can get the low speed. So this bandsaw can go from about 300 feet per minute up to 500 feet per minute up to about 5,000 feet per minute. And at the low end, you can cut metals like aluminium and stuff with, which I use it a lot for. This has the controls are up here, and this is on a magnet, so I can move them around. So I've got the on and off and the speed control there. Okay, over to the wood lathe. The wood lathe is a little wood fast, and it originally had a 1/2 horsepower motor under here, I thought I'd like to convert this to run with a variable speed. And originally I put a Huanyang VFD on it, but I've switched that over to a Powertran. And the motor that I had to, it was a single phase motor. And I looked around and I eventually found a wood fast 1 horsepower 3-phase motor under here. Now it's too big to go up there, so it has to go down here. And that meant, and the other problem was the pulley. This has got a 19mm shaft, and this one up here had a 16mm shaft, or a 5/8. And the pulley didn't have enough meat on it to enable me to use the old pulley and bore it out and put it on here. So I had to turn that pulley, make a new pulley for it, which was a bit of a pain. But this is fantastic. This is where I make all my bell mouth hoods. It's also got a tacho. There's the tacho. There's the tacho head there, and you can see the little magnet, and that's the magnetic head, and the tachometer is up here. This is the pressure switch for the a pressure switch here for the dust extraction control. Okay, I'll finish up with this. This is the dust extractor one up here. So the dust extractor's outside, and this is a 4 horsepower Huanyang VFD, and the control's been shifted down below. So that's the speed potentiometer, and this is a 3-position switch: 40 hertz, 50 hertz, and 60 hertz. This works extremely well. I'm very happy with the way that worked. Originally, it was a 3 horsepower motor, and I was waiting to get a 3 horsepower 3-phase motor, but could never find one. But eventually I found a 4 horsepower, and I've used that instead. And it's all worked out fairly well. Well, I think that's probably enough applications, and maybe we'll go back to questions.
Yeah, thanks for that, Bob. That made things actually a lot clearer, seeing all of those.
Yeah, when you see them actually in action, it sort of, I maybe should have started with some applications first, but let me just get this power back on.
Yep,
and the camera back the other way.
No stress.
All right.
You've got a hell of a shed, by the way. It's pretty impressive, all the stuff, especially with your space management.
Yeah, the space is an issue. I keep shuffling machines in. I get machines in, and I had a beautiful 1 horsepower pedestal grinder with 10-inch wheels on it, and it was I got it for nothing. This is once again a 3-phase machine that nobody wanted, and I converted it to VFD operation. Bought all these wheels for it, and then it just sat there. I bought another machine which I haven't got, which I converted to VFD, which I haven't got time to show you. But then eventually I gave that one to my brother, so I had to give a machine away so I could bring another machine in. So that's my policies. Nothing comes in unless something goes out.
Very, very wise. Do you have any questions, Gary or Garvin?
No, only Bob needs a bigger shed.
Yes.
Yeah. Oh, well, I have got, I've got 2 sea containers down at the tree lopper's yard where I mill timber.
Yeah.
And I'm occupying about a quarter of an acre of his, well, I was, I don't think I've got that anymore, is with the timber slabs and stuff. So I have got other spaces, but I really like working here, where it's, I can walk down after dinner, or if I get up early, like I often get up at like 5:30, and I wander down and I start something. I do a lot of things that require, constant attention.
Yes.
So, yeah. And I've got an electronics work area up in the house in my study as well. But that's another dangerous hobby.
Well, there you go. That was very, very interesting.
Sorry, where do you generally source your electric motors from?
Gumtree. A lot of them appear at the men's shed, and they try to move them on. Various people. About 7 or 8 years ago, 3-phase motors were extremely cheap, and you could get them for 20. I bought 7 or 8 of them for less than $30. Now these days, people are suddenly realising you can do this sort of thing to them. So the price of the used ones have doubled, and now you're paying $70 to $80. But I've got a cupboard full of them. Right? Let's have a look. You can see down in there. There's a few down in there. Oh, I must tell you about my favourite VFD conversion, which I haven't got time to really. Whoop, what's happened?
Huh?
Do you think you'll be able to find some use for this in the shed, guys? Or?
Definitely. It's convincing other people.
Yeah.
Or converting other people to see the value of it. Because our big issue is a big energy consuming dust extractor.
Right.
That runs 50% of the time when it doesn't.
I just lost Can you hear me?
Yes.
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 Hang
Yes.
on, where's the audio gone?
No, we've got you okay.
Oh, we can hear you.
Can you hear me now? Yeah. Sorry about that. I just ran out of battery on the mobile phone. Yeah, I was going to tell you about my favourite VFD conversion. I've got a very expensive coffee machine that I was given 15 years ago for a significant birthday. And it has one of these vibratory pumps, and it goes brrrr. Every time you make a coffee, especially if you've got company, you can't hear anyone speaking, right? And my wife was complaining a bit about this, and so I thought, I must change that. I looked around and I found this beautiful Swiss stainless steel pump. And it's the same as what they use on, you know, big coffee machines in cafes, big industrial, well, it was 200 litre per minute. It was ridiculous, right? I managed to get it cheap, and I had a 1/8 of a horsepower three-phase motor, which is only about, you know, that big. It's quite small. And so I played around with it, and eventually I thought, gee, this is very quiet, right? So underneath the cupboard, in a cupboard underneath the coffee machine, is a VFD, the little three-phase motor, and the stainless steel pump. And it provides the water up to, pressurizes the water up to the coffee machine. And hanging off the side of the coffee machine, I've got the speed control for the pump and pressure sensors and temperature sensors. And yeah, it's a sort of super geeky implementation, but it works really well. I really like it. Yeah. If the coffee's coming out a bit slow, you can tweak the pump up a bit and make it go a bit faster, and it pushes it out a bit quicker. Coming out too fast, you can back it off. So yeah, I'm recognise that if there's a motor and speed control needed, yeah, get a VFD. And I even helped a mate who had a big industrial commercial coffee grinder. It was a 1.5 horsepower coffee grinder. Imagine that.
Yeah.
Big, well, really big one, right? And he wanted to put a VFD on it or control the speed. And so he said, let's put a VFD on it. So we did.
So, Bob, when you say a three-phase motor, you're actually saying a motor that's designed to run in three-phase power.
Correct. Yeah. Yeah.
As opposed to just a
single phase. Yeah.
Okay.
Yeah.
I was surprised you could get a three-phase 1/4 horsepower motor. That's
well, the smallest one I've seen is 1/30th of a horsepower.
gosh.
Right, and it was smaller than my fist, and the wires on it were as fine as a human hair, right? And it was incredible, and it was from an industrial tool and cutter grinder. When you're grinding precision metalwork tools, you want zero or minimal vibration. So they could have used a single phase motor, but they chose to use the three-phase motor because they're much smoother, and so you won't have a jittering of the tool while it's being ground. You see, so you can they have actually made 6-phase and 9-phase and 12-phase motors, right? There were some German 9-phase motors around. Now you've got 9 wires, right? The chances of getting something wrong are horrendous, right? You get a very smooth output, but not that much smoother than 3-phase. The jump from 3-phase to 6-phase to 9 doesn't really gain you a lot of smoothness. Because going from single to 3 definitely get very smooth operation. Yeah. When I built when I exchanged the motor over for my dust extractor, because it was a 3 horsepower single phase to a 4 horsepower 3-phase, I used this vibration analysis app that you get on your phone, right? It's one you have to pay quite a bit of money for, but I use it a lot. And I was worried about the impeller being out of balance because I fiddled with the impeller a bit. So I had to measure the vibration, and I measured the vibrations of the 2 motors, and the single phase motor had more vibration than the 3-phase motor with the impeller on it.
and the impeller should be contributing most of the vibration. So it really shows you that, you know, the three-phase motors make a much smoother. They provide the power evenly as the motor turns around. There's always a constant force, whereas with a single-phase motor, it's a pulsed force, and that's what contributes to the vibration. Yeah.
One last question, Jackson, if that's okay.
Yeah.
Please. Yeah.
So the automation part is of obviously big interest to me.
Yeah. Okay. I didn't really dwell on that. There are a set of terminals that are the high voltage terminals, best left to the Sparky, right? But then there's about 7 or 8 of those. And then there's another set of terminals, which are the control terminals. And that's what you connect up the various switches, forward, reverse. You can have staged frequency steps, the potentiometer, and these all operate at between 5 and 24 volts. So that's very safe. You can't really damage yourself. You can damage the VFD, but they are incredibly robust beasts, considering they're made of capacitors and integrated circuits and so on. They look after themselves very, very well. But there, the control aspect, there's enormous, you know, I'll just show you a few. I haven't mentioned manuals, but this is the manual for an Ask Power VFD. This is $78 on eBay, and you get a 20-page book of few errors, hard to read. You know, the typical cheap budget electronics. You know, you really have to know about VFDs before you even start, right? So they are very challenging. And then this is the series of books you get with an industrial grade VFD. That's the big one I showed you earlier on. So this is the Honeywell, big Honeywell VFD. It's a big Honeywell VFD. So you get a book, it's got thousands of, you know, it's too much. But most of this is application. That's the user manual. That's the application manual, right? But very helpful. The applications really show you, because you can copy them, you see. Yeah. This is the one for the Huan Yang. It's 70 pages. And this is one on the Woodworkers Forum that we've, a lot of guys are using. And we think we found all the errors. There weren't that many, but there were some. Yeah. Like the maximum speed was the minimum speed and so on. When you get these things out of a box, you assume they're going to be factory set. No, don't assume anything. You've got to do a factory reset yourself, because you can have some problems. Yeah. I would not buy a VFD unless you could see the manual, because if that arrives and you don't understand it, you're stuffed, right? So if you ask your Sparky, can you put a VFD on this? And I found this $100 special on eBay. He's not going to be very happy about it, is he? Right? Because he's probably got no experience with it. The manual isn't worth anything, and he's going to be scratching his head, and he's the one installing it, so he has to guarantee it. So if you're working with some Sparkies, they may say, "Oh, we'll only use a Siemens or a Delta, or you know, and they're expensive, but you know they're very good too. They're industrial strength, right?" So yeah, definitely watch out for the manual. I've had so many inquiries from people. Can you help me interpret that? And I say, sorry, I don't know what to do. What's going on?
So last question. So do you program it via a PC interface, or you just on the keys on the?
Yeah, the programming is typically you dial up. So the programming is, it's not like instructions like a computer program. It's really what you're doing is setting a list of parameters. So it's called parameter setting. So you set the maximum voltage, the maximum current. You indicate what type of motor it is, what's the maximum RPM you want to go. what's the maximum acceleration time, what's the deceleration time. So there's usually about 20 parameters you need to set up. And if you're using the controls on the front of the VFD versus outboard, that involves setting some parameters. But usually it usually involves, you know, setting a bunch of numbers from 0 to 1 to 14 to 250 to 50 or whatever. So it's called parameter setting. And this VFD here has got like about 30 parameters, and the big Honeywell's got like 600. Now you don't have to set them all, right? But it can be very daunting. The Powertrans have about 300 parameters. It's very amazing what they can do. But it's all related to process control, right? Because you can hook up interlock switches and other things to them as well. And, yeah. Okay.
Very impressive.
Yeah, very impressive.
But if you want, you know, to come and have a look and see more specific, so you can see where all the things hook up and that, I'm happy to show you that as well.
Fantastic.
Yeah, wonderful. Thank you, Bob. And I asked you previously, but for the people that didn't watch the previous video, I know that you can be found on a woodworking forum. What was the site, and what was your username on that again?
It's woodworkersforum.com, and it's the Australian Woodworkers Forum. And my username is Bob L. Right?
Great.
Bob L. Yeah. And by the way, I've written this 2-page VFD for newbies. I think I sent it to you, didn't I?
You did, yes.
Yeah. And I've tried to summarise the basics in there, which people can contact me and ask me for if they want. Yeah.
Sure. Yeah, great. Alrighty. If there's no more questions, I might bring it to a close there with a big thank you to Bob. That was an awesome look around.
Bob.
No worries. Yeah.
Thank you.
Alrighty, everybody. I'll bring the meeting to a close. Thanks for all of your time.
Jackson.
And
Thank you.
Thank you.
you'll see your faces on Facebook in
Yeah.
short order. Alrighty. See you later, everybody. Bye.